This screencast involves solving inequalities that have multiple parts, and that could be both compound and or inequalities and absolute value inequalities. Let's begin with introducing some vocabulary. A compound inequality is an inequality that involves multiple parts. There are two basic types of compound inequalities, and or. The and type is what's in set notation we call an intersection, where two sets are joined, set A and set B. The or type is called a union, and that's where we have the elements that are in set A or in set B. So looking at the and compound inequality is only true. First part and the second part are both true. So, for example, x greater than or equal to negative 4 and x less than 3. We take x greater than or equal to negative 4, which on a number line has a closed circle on negative 4 and is to the right all the way to positive infinity. And then we look at x less than 3, which is open circle on 3 because 3 is not part of the solution or the set, and all the numbers to the left of 3. And if we combine those two together, the numbers that they have in common are all the numbers that are greater than or equal to negative 4, but at the same time less than 3. So the intersection of these two inequalities is the set of numbers between and including negative 4 and 3, but not including 3. So let's go ahead and solve an example of an and compound inequality. So if we have 3y minus 2 being greater than or equal to 10 and at the same time less than 19, our first step is going to be to use the addition property of inequality and add 2 to all parts. Our goal is to get this variable isolated in the middle. So the only difference between this and an equation is that we now have rather than two sides, we have 3 different parts. When we do that, we get 12 over here, we get 21 over here, and then just 3y in the middle. Next step is going to be to use the division property of inequality and divide everything by 3. Again, our goal to isolate the y. So we divide all these sides by 3, and we get 12 divided by 3, which is 4, 3y divided by 3, which is just y, and 21 divided by 3, which is 7. And that is our solution. Y is greater than or equal to 4 and at the same time less than 7. Okay, we're going to go slowly through this part of graphing the solution set for this and compound inequality. So y greater than 4 or equal to 4 is a closed circle on 4 and everything to the right of 4. Y less than 7 is an open circle on 7 because it doesn't include 7 and everything to the left. So now we're looking at the intersection of these two things. Everything that is both greater than or equal to 4 and at the same time less than 7. So we're looking at this joining, this intersection part. And indeed, we have a closed circle on 4, an open circle on 7, and everything that's in between. That is our solution. Now, an or compound inequality is true if either one or both of the parts are true. So, for example, if I have the compound inequality x greater than or equal to 5 or x less than negative 3, this is true. The solution is found where either one or both of them are true. That's called the union. So we get this by graphing both parts. X greater than or equal to 5 looks like this first number line. We have a closed circle on 5 and everything to the right of 5 all the way up to positive infinity. X less than negative 3 is open circle on negative 3 because it doesn't include negative 3, and it's everything to the left of negative 3 all the way to negative infinity. So the union of both these parts, the or, if we were to graph x greater than or equal to 5 or x less than negative 3, we wind up joining both of these things. And so the actual graph of this compound or inequality includes both parts. Let's take a look at a compound OR inequality. We have x plus 3 less than 2 or negative x less than or equal to negative 4. So we're going to go ahead and solve that step by step. And in this case, we really do have to, for ORs, we have to treat them completely separately. So we have x plus 3 less than 2, and we also have negative x less than or equal to negative 4. So first step here, we're going to use the subtraction property of inequality and subtract 3 from both sides. So we are left with x on the left side and negative 1, because 2 minus 3 is negative 1 on the right side. Over here, the second part, we're going to use the division property of inequality. And so we're going to divide both sides by negative 1. You'll recall in algebra that if I have a negative x, it's the same thing as a negative 1x. The 1 just doesn't appear by convention. So we're going to divide both sides by negative 1, but remember, from a previous screencast, if we're dividing or multiplying by a negative number, we do have to change the direction of the inequality. Therefore, less than or equal to becomes greater than or equal to. So the two parts of our solution are x less than negative 1 and x greater than or equal to 4. Let's go ahead and graph that. So we're going to graph the first part. X less than negative 1 is not including negative 1, so an open circle on negative 1, and everything to the left of negative 1. X greater than or equal to 4 includes 4, open circle, closed circle on 4, and everything to the right of the 4. Our solution is the joining of those two, the union of them. We have everything to the left of negative 1, not including it. We also have everything to the right of 4, including 4. So absolute value inequalities are cases of compound inequalities. If we have the absolute value of something being greater than a number, for example, the absolute value of 4x plus 5 being greater than 7, that's actually an OR compound inequality. Because what's in that absolute value bracket can either be greater than that distance from 0, in other words, to the right, or it can be less than the negative of that number on the negative side of the number line. For example, 4x plus 5 could be greater than 7 away from 0, or 4x plus 5 could be less than negative 7 away from 0. So we have to deal with that as a compound OR inequality. In a similar way, the absolute value of something less than a number means that that distance is closer than whatever that number is to 0 on the number line. For example, the absolute value of 4x plus 5 less than 7 means that 4x plus 5 is within 7 of 0 on the number line. In other words, it's both greater than negative 7, to the right of negative 7, and to the left of 7, less than 7. We treat this as an AND compound inequality. So absolute value inequalities are treated as compound inequalities because they do have two parts, they have multiple parts to them, and we have to deal with those parts either as an OR situation if the distance is greater than a certain number, and then it's an AND situation if the distance is less than. We're going to look at this first example in the screencast. So suppose we have the absolute value of 2x minus 2 being greater than or equal to 4. That means it's more than 4 away from 0, or exactly equal to 4 away from 0 on the number line. And we want to graph that solution. So we would write this as two separate statements. Just like we did in solving absolute value equations, we would write that into two parts. We do the same thing with inequalities. It's just that the first part, 2x minus 2, is now greater than or equal to 4. Or 2x minus 2 can be less than or equal to negative 4. So we're going to solve each of those inequalities step by step. First thing we're going to do, we're going to go ahead and use the addition property of equality and add 2 in both parts, in both separate inequalities to all sides. That's going to get us closer to isolating the x. Getting rid of the 2 on the left-hand side here gives us just 2x. greater than or equal to 6. 4 plus 2 is 6. And then over here we get 2x also being less than or equal to. Negative 4 plus 2 is negative 2. So here's the two parts of our compound inequality. The next thing we're going to do is use the division property of inequality and divide everything by 2. Reason for that is the 2 is being multiplied by x, so we want to divide by 2 to get rid of it. So on the left part here we have 2x divided by 2, which is x, 6 divided by 2, which is 3. So the left-hand inequality is x greater than or equal to 3, or 2x divided by 2 is x, and negative 2 divided by 2 is negative 1. We don't have to change the direction because it is dividing by a positive number. And this is what our solution looks like graphically. It's all the numbers less than or equal to negative 1, and at the same time, or at the same time greater than or equal to 3. So both are less than or equal to and greater than or equal to, so we got two closed circles here going to the left of negative 1 on the number line and to the right of 3. And that's our solution. This screencast dealt with solving compound and or inequalities, including those involving absolute value.